My name is Dinesh, and I work at Microsoft. So the opinions expressed here are solely my own, and it does not necessarily belong to my employer. Um, so let's start with a typical use case of applying eBPF. Say I, as a security researcher, want to log all the syscalls invoked after a specific incident. It could be execution of a binary that I want to analyze. It could be a malware, or it could be something that I am trying to do vulnerability research on it. And I want this to happen non-intrusively across the system so that I should be able to record the raw data points, which can later be used to create insights or to act as a base data for creating deep learning tools or any other research frameworks. If you see, it would be something similar to Regshot for Windows. Regshot is a very popular tool, as many of us would know. In Windows world, where before running a malware, we would run Regshot to take a pre-snapshot and then run the malware and then take a post-snapshot. It will capture all the file systems, Windows registry before running the malware and after running the malware, and then do a comparative study to get a report of what has actually transpired while running the executable. So at the outset, it might seem very simple, and in fact, it is one of the common use cases. However, let's take a deeper look. So this would be a typical flow where we would take a snapshot, pre-snapshot, capture all the files in the target system, and then kernel data structure and other significant files that corresponds to certain automatic actions that can be done, like scheduler. And then we will run the binary. Then we will again take a snapshot. We will make it pass through an active noise filter that captures, that eliminates all the common events that happen as part of the normal system execution. And in the at the end, we will get a system report. So and this has to happen non-intrusively. If we can quickly take an analogy of Heisenberg's uncertainty principle, right? Like Heisenberg particles. Very famously, we used to hear you can either know where the particle is or how fast it is moving, but you cannot know both. The reason being that the particles are so sensitive. In the process of measuring it, you would be displacing it. You would be emitting light on those particles. Those particles are so tiny. The projection of light on them displaces it. How we calculate the temperature of water, say for example, if we put a thermometer in the water, the thermometer actually draws heat from the water to show the temperature. In this case, it is negligible because the water body is large and the values are larger, and the amount of temperature the thermometer draws is negligible. So similarly, when you want to do some real-time event analysis for security observability problem, you have to take this into consideration, that you are not intruding in the normal flow. And more than that, there are certain limitations with the ptrace and LD preload, which are like typical hooking techniques for process-specific interception. And more importantly, the ability to handle polyglots. We will quickly discuss what is polyglots. So specifically, we will talk about Golang. Golang, as we all know, is a ultra compatible modern language. Just with a single build script, it can generate 40 different executable that can run on 40 different operating system and architecture combo. So it has such a powerful cross-compiler support from the same system. You will be able to generate for many number of flavors and architectures. So naturally, it's a great choice for security researchers, and automatically it makes it as a great choice for malware authors as well. We have been seeing a constant increase in the malware which are generated by Go language. So one of the key challenges that Go language built executables pose to security researcher is that If you try to do typical ptrace on them, you would get this message saying that unable to inject library into the process because it doesn't have libc in it. So for this demo, we have taken some 7 languages and built a hello world program. It simply reads a file, and we want to put a typical hook and then see how do these executables behave. And we will then run the same demo with the eBPF to showcase how seamless it can become to observe something without much effort. So for the benefit of in the benefit of time, because we have only 15 minutes, I have already recorded these demos. Let's quickly skim through these demos. Say, for example, now let's ptrace an executable which is compiled with C language compiler. You run it and you observe it. So you just put a ptrace hook, and everything works fine, no problem. But if you want to do the same thing for Go, so now what you do is you try to put the same ptrace attach, and you get the message that it is not able to inject into the library. The same thing would happen if you try to attach a GDB. You can't break on the library call like how you typically would do for other executables. So now let's do the same demo with OpenSnoop, which is one of the eBPF utility. And in this case, you can just start the probe, set up the probe, and then you can start to run all the 7 executables one by one. And you will be able to observe that BPF probes doesn't have any issues with respect to tapping all the syscalls that is executed by these executables. So it is kind of non-intrusive, and it doesn't need to go through a lot of efforts. You just place the probes and then get the results. So now we have established the base. Let's observe a ransomware execution through eBPF probes. So the goal for us in this exercise is to reconstruct the flow of a multi-component file encrypting ransomware. In order to make it more interesting so that we can showcase the power of eBPF and the smoothness with which we can collect various probe information, we have developed each of these components in different language. For example, the file dropper is written in Rust, the downloader which the dropper drops is written in C, and the downloader eventually pulls up a file encrypting ransomware which is written in Golang. So in order to run this demo, we have set up this lab environment where we are running, we are hosting the file encrypting ransomware in one of the made up CNC, and then this is the victim machine, and there are some other machines in the same intranet. So let's quickly see this demo. So as you could see here, we are setting up some of the probes for open syscalls, and then executable is nothing but it sets up sysclone syscall tabs. And once all these probes are set up, we can run the dropper, which will start a chain reaction of dropping and then downloading and then encrypting the files in the disk. So now let's start the dropper. And as you could see, all the information is captured. And in order to make it more intuitive, let's plug the graph module to the eBPF output. Basically, what we are trying to do is once we have established the probes and the trace points, the output that is streamed by those probes and trace points are plugged into the graph module, where we use a Neo4j as our backend. And the information streamed by these probe BPF trace and OpenSnoop and execSnoop, we are converting it, we are representing the knowledge as a triplet. A triplet is nothing but we are representing entities, and then the relationship between entities is represented as edges. So this naturally builds a knowledge graph organically, so that for an analyst it will be easier and intuitive to reconstruct the execution flow. Let's quickly see that in action. So in this case, you could see that all the information are actually captured in triplets and then converted into nodes and edges. So during the execution of this ransomware, there are 6 processes. So you see 6 nodes here. You can start from the bash, which started the execution, and it has dropped the dropper. And when you expand the dropper, it has downloaded the payload zzz.bin, and the zzz.bin is again downloads payload.bin, which is the Golang written binary. And if you expand the payload.bin's image path, you get to see that it is actually touching all these files, which are nothing but the GOAT files that get encrypted by this file encrypting ransomware. So now you will be able to intuitively associate the relationship and how this executables accomplished the task of infecting the machine with file encrypting ransomware. So with that, let's quickly move on to the Android part. So eBPF and Android has been talked about a little in the community, but it is a little challenging because the kernel, in order to make Android's kernel to support eBPF, it requires some of these flags to be compiled with while we are building the kernel for our target machine. In this case, we are using Pixel 4a, Pixel 6a, and emulator that runs Android 12. Pixel 4a was running Android 12, and Pixel 6a was running Android 13. So these flag details are provided in the BPF trace repositories page as the check kernel features. So once we build the kernel that supports the eBPF modules, we can really make use of the rich tools and the powerful tools it produces. That is where the analogy that I gave about observing something without disrupting the actual values. Because when it comes to Android, because of the restricted ecosystem, the monitoring and the security observability becomes a little difficult because we often end up slowing down the system. But in this case, the slowdown is not significant. Let's quickly see 2 demos. So once we have established the K-probes, say in this case, we are using BPF trace front end, and we are setting a trace point on syscenter open at syscall. And this is not something that you can limit with one syscall. You can use as many syscalls as possible, and then you run a executable. You run an Android APK file which is protected by commercial protector, or you want to do vulnerability research. You want to see what files it uses and how it uses. So you will be able to trace it seamlessly. In this example, as you could see now, we have set the trace point, and then we are starting the SMS application, and we will be able to see it, how all the different syscalls that gets called as part of the execution of the file that we want to analyze. And similarly, we can use a real device and observe the traffic in real time using TCP Connect. So as you could see here, now we are setting up some open syscall tapping using OpenSnoop and execsnoop for sysclones, and then TCP Connect, which is also a BPF helper utility. Now I run the actual browser in the device. Actual browser in the device, and then we browse to eBPF.io, and we can see the traffic in real time, how it is captured. Yeah. So I hope we have covered quite a bit of ground in the limited time we had. So I'm open to any queries you may have. This is a very interesting framework, and I have been trying to learn it for the past few months. So yeah, I'm looking forward to learn together with the community. Thank you, everyone.